young.
Got some assignments up for 1.4. I want to just give you a little bit of extra background, fill in a couple blanks, and then you're good to go. All right, so I'll introduce you to an interesting function that you may or may not have seen before. It's called the greatest integer function, and it's typically written in one of two ways. If you have these kind of weird double brackets with an x in the middle, that's one way that it's sometimes represented. And the other way, like on your calculators, is the function int of whatever the argument is, okay? So what does it do? Well, the greatest integer function is an example of a step function. It's a function that is defined as having the value of the greatest integer that is less than or equal to the input, okay? So for example, if I input 3.1, what would the greatest integer function output? Be 3, right? So the greatest integer that's less than or equal to the input, okay?
And it has to be one.
It has to be an integer, yeah, greatest integer. So what about 3.9999999? Be 3. What about 4? It'd be 4. Okay, what about negative 0.5? Negative 1, right? Okay.
Zero.
Negative 0.99999. Negative 1.1.
Oh, -2.
Negative 2. Negative 1.
What?
Negative 1.
Because
Right.
it's going backwards that way.
Okay, so if we were to graph that thing then, what's that gonna look like, that greatest integer function?
Oh, it's just gonna be like.
So let's say these are the x and y axes, and we're just the solid, these are kind of horrible graph paper. I wish they just didn't have all this little stuff in the middle, but we'll say that the dark lines are go by integers. Okay, so where am I gonna be at 0? At 0, good. So when x is 0, y is 0, right? Agreed?
Yeah.
Okay. As x increases, y stays at 0 until 1. And then we jump up to the next step. See how that works?
There's breaks in functions.
Yes. So this is, and it just continues thusly ad infinitum.
It steps without a wall
Right,
where
it's
you
the-
It's cool mountain steps.
Right? It's an infinite staircase, okay?
except without a whatever.
The risers? Right,
Whatever.
exactly, yeah. Okay, so we could define, while we're at it here, let's define just a slightly different function. This is called the ceiling function. This is another important function. So like usually on a calculator or a computer, it will look like that. A lot of times it's written, whoops, like that. What do you suppose the ceiling function is?
The highest value.
Where you would grab that.
So it's gonna be, for every input value of x, it's gonna be the least integer that is greater than or equal to x.
Why ceiling?
Down.
Up.
That's ceiling because it's pushing it up to the next integer. See what I'm saying?
Raising the roof.
So a ceiling function would look like, it's one that would go over, like, it would have been a little different. How, let's do this. Let me go.
It'd be like 0 and then it'd start at 1.
So the ceiling function then, I'm just gonna, so there's the y-axis, there's the x-axis. The ceiling function at 0 is gonna be what?
1, 0.
At 0, it's gonna be 0,
Oh, 0.
but at 0.1, it's gonna be 1. Yeah, like at
Oh.
0.0001, it's gonna be 1, right?
So.
Right, because it's the least integer that's greater than or equal to x. Okay, does that make sense? So it's pushing it up. So it's gonna go like this. Very similar, right?
Stairs.
Yeah, exactly. It's just that the hole is pushed to the,
Towards zero.
whoops, what'd I do? I messed that up, didn't I? Those are, okay, I messed up. Should be, except now the hole's on the right.
No, that doesn't make sense.
Wait, that's the greatest integer function.
Oh, what did I, yeah, I just totally messed up.
Oh, gosh.
Like,
That's right.
You had it right, yeah.
You
I
thought
had
you
it
were
right
doing that.
until there, but then I messed it up here. Should be like this,
oh.
right? Like that. That makes sense? So the hole's on the left side instead of the right side of the step. Okay, and the step start at a different place, right? There's ceiling function, there's greatest integer function, sometimes also called the floor function. Okay, same thing, right? And so sometimes, like up here, we could write it this way, or sometimes they'll write it as floor of x, or they'll write it like that. Okay, they all mean the same thing. Here's a way to think about this. It's kind of a cool model. Think about like if you had a string that had knots on all of the integers, and you had beads. Right? So we're going to put the value of a number, so we're going to put it on the number line as a bead. The greatest integer function, or the floor function, is always going to push the bead to the left until it encounters a knot, right? Ceiling function will always push the bead to the right until it encounters a knot. Does that make sense, what I'm saying? Okay. All right, so then what is going to be, let's try an example here then. What is the limit of, oh, and I'm going to show this to you on your calculators too. That's what I forgot to do. So on your calculators, oh, not there, right there. So on your calculators, big output, okay? So if you go y equals, need that stuff. I don't think so. Okay, so the greatest integer function, where do you find that? I think you can find it in a bunch of places. One place you can always find everything, I should show you this, is the catalog. So if you go second catalog, that gives you every function on the calculator. Okay, notice that I've got an A highlighted up here, which means I'm already in alpha. And so if I just type the key corresponding to the alpha I, it takes me down to the I's, and there it is, INT. Okay? That's not, so everything is on there. So it's an exhaustive list. Maybe you don't want that big a list. Then you can always go through the math screen. We'd go math. Oh, that's what that looks like. That's not what that looks like, is it? Oh, I think I just need to get out of catalog first, maybe. Okay, so if I go math, yeah, there we go. I believe this would be on the number menu. Yeah, it is. Okay? Make sense? And then I also think there's even a shorter shortcut. If you go alpha, maybe F3? No, F2. Alpha F2, oh no, that probably won't do it. I'm sorry, I've only got one shortcut for you on this one. There is no alpha shortcut. So once again, math screen, and then math divides up all kinds of functions into their various kind of categories. Math is going to be things like, these are going to be things like finding a function's minimum or a function's maximum, or a derivative, right? Which we haven't gotten to yet, but we will, or an integral, okay? Number or numerical, if I scoot to the right, this is going to be things that you can just calculate these quantities for a number, like absolute value, or you could round something, right? It's going to give you back, you're inputting a number, it's giving you back a number, right? Complex numbers, of course, whoops, you know what that is. I mean, that's just dealing with, complex numbers that have presumably imaginary parts. Probability stuff, it's n permutations, take an r at a time, etc. There's the factorial. And then fraction menu you're already familiar with, right? These are all the templates you can use for fractions, mixed numbers, convert between fractions and decimals, et cetera, et cetera. But we want the number one, right? So if we do this, if we go number, and we go 5, and we put in greatest integer function of x, and I hit zoom 6, look what it does. Okay, it looks familiar, right? Let's pare down this window just a little bit. Let's have the window, how about if we just go from -4 to +4, and then if I want to make the window auto size the y's based on my choice of x restrictions, my choice of domain, what do? Zoom 0, which is zoom fit. Okay, so zoom 0. And then it'll choose the y's so that my function is displayed using the entire vertical aspect of the window. Okay? That looks pretty good, except that's slightly different than what we drew. What's it missing? It's missing the holes. So how do you suppose you know where the holes are on this function using a calculator? Yeah, you could. There's another way too. We could just test values, right? We could just go like, remember our shortcut for testing values? The long cut is second, calculate, and then these are all the things I can do with a graph. I could go value, and then type in 1, for example, and hit enter. Look where it puts me. It puts me on the left edge of that segment, so the right edge must be the hole. Does that make sense? Okay. The shortcut for that is, if I've got a graph, I can just hit trace, and then enter the x value, and it assumes I'm wanting to evaluate a function. And so look, when I get to the right of that step, once again, it pops me up to 2. Okay, make sense? Okay. I want to see if they have one other function on here. If we go over to number, so they have integer, let's see if they have a floor function. I think they should. But it looks like they don't. Wow, that's really bizarre. I will. Yeah, I'll check out catalog. That seems really strange to me that there wouldn't be. Okay. No, that wouldn't be it. Huh. Let's try. Just want to try something. Oops, I want to get out of graph. So let's try this again. Math, integer part. Oh, I know what I did. Okay, so that's not going to work. Let's try catalog. Well, that's really bizarre to me that they wouldn't have that. Don't have it. Wow.
Is there a program online that we can download for
Why don't you find out for me?
Wait, didn't you
Yeah, that'd be good to know if there's a.
Wait, didn't you just do the floor? You just did the floor.
Don't we need the ceiling?
I mean ceiling. Oh yeah. I did floor. You're right. So I need ceiling. But that wasn't on there either. So let's try that. If I go C. Yeah, you're right. That's the one I was missing was ceiling. But they don't have the ceiling function.
Would it be called ceiling function?
Yeah, it would. Let's try.
The ceiling command.
Let's try catalog.
Yeah, this looks to be it on TI Basic Developer. Ceiling command rounds number up to most for at least as large.
If you go
as
back to
number
math
is ceiling
on
five.
mine, it says like you use the I part, and then number 5 on mine is just INT, and that's the one that comes out -3.1 comes out -4.
Negative 3.1 should come out. So the ceiling function for negative 3.1 should be -2. And I just wasn't seeing a way. I mean, we don't need to waste. I mean, that'd be. You guys look into that. School me up.
I found it, bro.
So you found like a downloadable thing if you go to the TI.
Yeah.
Okay.
Do you want me to go get some parts from Jones?
Not today. Next, because it's a short day. But otherwise, yeah, we will. Because that'd be nice to have. Be nice to be. And I think there are some little modules where you can download some extra functions and things.
You can also download on these.
Oh, that's good. Okay. Well, that's. I've been dying to. Thank you. I've been really looking for that. That's good.
Yeah, you know.
Yeah.
Pokemon Go or
Okay.
Oh, Pokemon, no. Yeah, Pokemon Go.
Okay. So then try this for me. Let's see. How about if we want to do the limit? How about if we want to do the limit of
Why not? They already
int
did
x as x approaches -2? What's my answer?
Negative 2. Wait a second, so
Well,
that's, is it,
Ignore the bottom two.
so does that mean if it depends on which?
Yeah, what's the answer to that? What's the limit of the greatest integer
It's-
function
it's
of
not-
x
not-
as x
not
approaches -2?
Undefined or what?
It's no limit.
No
Yeah,
limit.
it's
Yeah.
no limit.
Get wrecked, suckers, noobs, get good.
why?
Look at the graph,
You know what, River?
picture the graph.
Let the math be here.
Well, yeah, but what's happening at -2? Guaranteed. There's a break in the function, right?
Oh.
Right? And so the limit is undefined, okay? But all is not lost.
But
Well, it's not well-
That changes
but-
things.
Well, we could just stick with no limit.
What's the answer to that one?
Wait, is that from, that's from the right?
That's from the left.
From the
the
left,
negative
it's from the negative direction.
Oh.
So it's -2.
No,
Would either of them be
negative
-2?
Negative 3.
No, oh,
Negative 3.
I don't know.
So
Because that
remember
means
what the greatest integer function / floor function does. It's the greatest integer that is less than or equal to the input.
Yeah,
So I'm putting in a number, when I put in -2 minus, what's that like putting in?
Negative 3.999.
No, negative 2.00000001, right?
But it's approaching from the left.
From the left. So if I'm approaching -2 from the left, I'm approaching from values that are slightly more negative than -2.
Oh, right. yeah.
Right? See what I'm saying? Okay, so if we go back to our picture, we're gonna be approaching -2. I guess maybe I should put one more stair on this, huh?
But that's the ceiling. aren't
No,
we?
it's not. That's just where I wrote down ceiling
Oh.
function. Remember, this is the floor function, greatest integer function. Because look, the beat has been pushed left. Okay? So if I'm approaching -2 from the left, I'm approaching from this direction. So the ant is, right, he's walking towards a value that he thinks is gonna be y equals -3. See what I'm saying?
Yeah.
The ant walks along this step towards a value of -2, but don't lose sight, and this is, people always wanna do this. Remember, a limit doesn't really care about, it doesn't, well, we shouldn't say that. In the limit, we never take that final step, right? It's about where the ant anticipates stepping when it gets there, right? And so the ant anticipates stepping on a y value of -3. Okay, so the answer is -3. Well, what about this one? As x approaches -2 from the right, that's gonna be a value like, no, it's gonna be like -1.999, right? See what I'm saying? And so that's gonna be slightly more positive, and so then what's the answer gonna be? -2, right? Okay. Okay, so what else? Okay, I want to identify some things here. So let's attach some labels to stuff. And this is an online textbook issue, and not necessarily your Larson textbook issue. Okay, this is a little different. It's neither one is. I mean, this is just some extra information. So types of discontinuities. Okay, so types of discontinuities. Now, we already talked about this, right? We said, but I want to use the language of Math Excel for School for a second. So we have an infinite discontinuity, which is going to be an asymptote, right? And that's one place where we said a limit doesn't exist, right? Okay. So we associate that with a vertical asymptote. We had a jump discontinuity, which we associate with a finite break. And then we had that weird one, which was oscillating. Remember that one? We looked at the sine of 1 over x, and it just oscillated phonetically in the middle, and so there was no limit there. Okay. The other kind we had, type of discontinuity that we've just introduced, is a point discontinuity. And that would be like a hole in a function, or a hole in a function with one point that's maybe above or below it. Okay. So these fall into two general categories. All of these top three are called non-removable, and the bottom one is called removable. Here's why. The definition of a removable discontinuity is one that can be repaired by adding or moving a single point. Okay. A non-removable discontinuity is one that would require us to redistribute an infinite number of points.
Wait. So with the point, you're saying that that's for ceiling and floor functions?
No, no, no. The ceiling and floor functions would be considered jump
Okay.
discontinuities.
Right.
Okay. So, does that make sense? So this fourth kind here, the point discontinuity, that's really one of two things. It's either this or that. The dot could be below or above, right? But in either case, all I have to do is either add a point or move a point. And that's it, one point though. And I repair the discontinuity. All of the other ones would require me to move an infinite number of points. Obviously a vertical asymptote would, right? But even like a jump discontinuity, if you look at, let's look at this possibility. If it's a jump discontinuity, then we still, how many points would have to be moved to make that a smooth transition? Infinite number, right? You could say, well, just bend that one, just bend that little segment down there. Well, yeah, but any interval on a function, no matter how small, if it's an interval, contains how many points? Infinite, right? Okay, get the idea? Okay, so then, given that, let's look at some examples of functions with removable discontinuities that we could remove. Okay, so for example, how about something like this? Let's take the function, how about f of x equals x squared plus x minus 6 over x squared minus 5x plus 6. Okay. Are there any, let's find any discontinuities on the function about. Okay, so we could, and you're getting that by factoring top and bottom. Okay, so if we factor the top, what do we get? X plus 3 minus 2. The bottom we get x minus 3, x minus 2. Okay, so give me, so where is it discontinuous?
Positive, negative 3? Well,
No.
again,
Positive,
Positive,
positive 2, and because.
Positive 3 and positive 2. Okay, good. So f of x is discontinuous at x equals 3 or x equals 2. Okay, so describe those discontinuities for me. Which of those is removable and which is non-removable? 2 is removable. 2 is removable, that's right. So this is 2. This one is a removable discontinuity, whereas at x equals 3, that's non-removable, right? I don't think I'm supposed to hyphenate that, but who cares? Right? How come? Okay, because the x minus 2's cancel algebraically. Remember what we said? I think we just left off with this maybe on Friday. You probably knew this before, but maybe we've never made this connection. Intuitively, you probably knew this. So whenever we have a shared 0, top and bottom, those are the types of discontinuities that we dealt with already as a limit with indeterminate answer, right? In indeterminate form. And we always were able to come up with some alternate function that agreed with the original everywhere but at that one point. Essentially fill in the hole and take the limit, right? Does that make sense? So this one we know because it shares the same 0, it is a hole with the point discontinuity. This guy over here, though, is not, because if I were to take the limit as x approached 3, we would have gotten a number divided by 0, which we recognize as being a vertical asymptote, right? So it's non-removable. If we want to be more specific, it's infinite. It's a vertical asymptote, right? Okay, so now what if we want to go one step further? Let's say that we want to define f of 2 in such a way that this function is made continuous. Okay, at least on that one interval, at least at 2. Okay, so we want to fill in this. We want to remove the removable discontinuity.
Can we just do that without crossing out
Okay, well, we almost did. So yeah, let's take that one step further. So let's take this guy. I want to treat this very carefully because it's so easy to let you're smart, so you already kind of seeing the process to go through to answer the question. But let's not confuse the answer to the question with the actual reason that is the answer to the question. Okay, and they're different things. Sometimes I think the reason gets bypassed in favor of just getting the question answered. So once again, the goal here is we want to define f of 2 so that f is continuous at x equals 2. All right, so as of right now, we have a hole there, correct? In order for us to fill in the hole, we need to figure out where the ant anticipates stepping and give the function that value, correct? Does that make sense? Because right now, if we write down f of x is only defined where x is not equal to 2 and not equal to 3, right? So then we're going to define maybe some new function. Let's call it g of x. So g of x is going to equal f of x for all x not equal to 2 or 3, right? Okay, but we want to give g of x the right value so it fills in the hole at 2. That's what we're being asked to do, right? You guys know the math for this still. What do we have to take? and you told me back here, well, we did this by crossing out the negative twos,
Can't we just,
but that's a part of a process.
f of x times x minus 2 over x minus 2?
Yeah, but what's that process called? What are we really doing? The function f of x is undefined in 2, right? But we want to know, we know that it's a whole, right? So we know that if I were to graph this function, we know that at 2, we don't know what the function looks like, but that's a whole. And then it turns out at 3, well, we've got something weird going on at 3. We don't know if it's what kind of vertical asymptote it is, but we won't worry about it. This is what we're worried about anyway. We know that's a whole, so we want to be able to fill that in. But to be able to fill it in, I've got to know what? How do I know what y value to assign? See, I've got to be able to say, okay, when I've got to be able to, yeah, I got to take a limit. Exactly. You see that? You see that?
Oh, snap.
And so that's why I object to the idea that, okay, we didn't already do it by crossing these out, because mathematically what we're doing is we're solving the limit. We're going to take the limit. In the process of taking the limit, yeah, we're going to cancel those factors, the offending factors that are causing the indeterminacy, right? And that's going to give us the answer. But then the answer to the limit of f of x has to be the value we assign to the function if we want to fill in the whole. Right? You see what I'm getting at?
Just like f of 2 equals.
Right, so we'll do the problem. Let's just see what we get. So if we take the limit of f of x as x approaches 2, and here's something else I gotta tell you guys, you gotta start doing. I'm watching people do work, and when they're taking limits, did I mention this last week? I think I did. Yeah, you gotta keep that limit notation until you actually take the limit, until you evaluate the limit. Otherwise, that would be like, on the test, I will mark you wrong on that, because that's at least partially wrong. So the limit of, we already factored this, right? It was x plus 3 times x minus 2 over x minus 3 times x minus 2. As x approaches 2, those cancel. And so we end up with, now we can take the limit, we get 5 over negative 1. So negative 5, right? That's the y value of our whole. And so we got the answer. We need to define f of 2, right? So g of x then, when x equals 2, needs to be defined as what? Negative 5. Okay? Oh, that was tight. Okay? That gets you most of the way there.